Hey people, I wanted to give you a solved example of a coefficient of friction kind of problem. So, we're back to Homer dragging the stone of triumph. And we're given, well, how much tension is on a chain, the angle, a coefficient of friction. We want to know what the stone's acceleration is. So, our problem still starts with a good free body diagram. All right, we got an mg. We got a tension and an angle, which makes our normal a little smaller than mg. We got a friction force. All right, this one's pretty detailed. There are a lot of elements that we're going to have to keep track of. Um, but the nice thing is that it starts with the same types of processes that we'd have in any dynamics or statics or any kind of forces problem. So what's the stone's acceleration? Well, that's going to happen in the horizontal direction for us. So I'd start the net Fx is max. All right, that gives me Tx minus the friction force equals max. Well, right off the bat, now that we're given the coefficient of kinetic friction, what I'm going to do is go ahead and, well, first let me write this as T cosine theta. Write this not as friction force, but as mu times normal force. Well, and if you want, I can write the K and the K here. Not the most important, not the most important part in the world, those subscripts. That's better, it's not any better. So there's our next step. Okay, you do have the option of, off to the side somewhere, figuring out what friction force is, and then pumping that back into there. That's certainly an option. I'll do it all at once and come up with the single expression. Now, the problem here is, or at least the next issue is, well, what's the normal force? All right? And the thing you'll get familiar with any coefficient of friction problem, what you have to end up doing is doing an analysis of forces in the vertical direction and the horizontal direction. Or maybe I should say, in the horizontal direction and the vertical direction. Here's our horizontal direction stuff that involves friction force. But then we need to look at what the normal force is, and that's a net Fy thing. All right? Now, for this situation, this is an object being accelerated across the floor. So let's go ahead and state that vertical acceleration is 0. So this gives us normal plus Ty minus mg is 0. Or normal equals mg minus t sine theta. Ty is t sine theta. All right, we got to be careful here not to just say that normal is mg. Sometimes, but not here. So if we want, well, what we can do is take all this stuff and pipe it into here for the normal force. If you right now want to actually calculate the value, the numerical value of the normal force, and then plug that number in over there, fine, no problem. Okay? But I come up with the following big old expression, T cosine theta minus mu times mg minus t sine theta. Well, that would equal ma. Well, I'll just write equals ma. But we want a, so we divide the mass out of both sides. Okay? That answer, give me a minute, I'll get back to you. I get acceleration equals 0.34 meters per second squared. And that's using g as 9.8 meters per second squared. Okay? If you want, let's see, what's mg? If we do mg with 9.8 for g minus E 400 sine 30. So this gets you 780 for the normal force if you're just plugging that into all this stuff. Okay, so that's not as hard as they come, I guess, but it is certainly a bit of a complex one because of a couple of things. Certainly one is the fact that we have the coefficient of friction, and two is, well, we got to make sure that when we're talking about what the normal force is, we have to take into account that there's a vertical component of that tension force. Okay, there's one example. Just remember your general process. Free body diagram, check. Net force statement, well, check. But now that we have a friction force written in there, well, here's how we express the magnitude of a friction force, mu times normal. All right, and then the process is, well, what's the normal force? That means we're going to have to typically do a net force in the y direction statement. Okay? Okay, folks, see you soon.